welcome everyone back to the second day. This is the morning session. And the first talk we'll have Rosa Valenti from University of Frankfurt and talking about exploring non-local correlations in iron-based superconductors theoretical approach. So Rosa, the floor is all yours, I guess.
Yes, thank you very much, Ming, and thank you very much to all the organizers for the opportunity to present our results. So today I would like to discuss the possibility of the role of non-local correlations in iron-based superconductors. And as I was telling to Himiao, since I am in a session where topology is an important topic, I would like also to present very recent results on prediction of double Weil points in these materials. First of all, I would like to thank my collaborators, so especially Karim Santu and Stefan Backes for the work on non-local correlations, as well as Niklas Heinsdorf, Morten Christensen, Mikel Iraola, Turan Birol, Rafael Fernandez, and Christian Batista for the work on Weil points. So if we consider the generic phase diagrams for the iron-based superconductors in a temperature versus doping or pressure representation, we know that we have a superconducting phase in the vicinity of some magnetic phase or phases, nematic phases, structural phases. And along the years, we have been having new type of phases coming into these complex phase diagrams, which are a consequence of a subtle interplay of charge, spin, orbital, and lattice degrees of freedom. And what I want to concentrate today is on the role of local versus non-local correlations in some of these phases, as well as possible new topological states that can emerge in these materials. And let me start with correlation effects, how important are in these materials. So we start with a description of a non-interacting electronic system. So basically we can describe the system in a K representation, so in the reciprocal space representation, as basically having quasi-particles that have an infinite lifetime. And now when we start to switch on correlations, a strong interaction among these quasi-particles, what we observe is a transfer of a spectral weight in what we call the lower and the upper Hubbard band. And the way of mathematically describe this process is, for instance, when we consider a Green's function representation, is in terms of a self-energy, which has in principle momentum and frequency dependence. So what about now focusing on the iron-based superconductors? Where do we see traces in experiment of these electronic correlations? And of course, there is many different probes to just observe these correlations effects. I will concentrate mostly on angular resolved photoemission experiments where one sees strong band renormalizations, but there are many other experiments like the Haas-Van Alphen, optical conductivity, thermodynamics. So for instance, Himiao did at the very beginning of the iron-based superconductors together with his colleagues, a very nice investigation of the effects of correlations by just looking at optical conductivity experiments. So just to show you that this discussion of correlations in the iron-based superconductors is just a discussion that already started in 2008. So what I want to do today is concentrate on these renormalization effects that we see in angular resolved photoemission experiments, and to just see how strong bands are renormalized. I will first concentrate on lithium iron arsenic. This system, we had yesterday a very nice talk about recent Ironbase measurements on this material. It's a nice test bed materials to, in fact, investigate these correlation effects, because the system doesn't show a structural phase transition, doesn't show a magnetic phase transition, doesn't show nematicity. Basically, it's a system in the tetragonal phase that goes superconductor at 18 Kelvin. And as you can see, these are Ironbase measurements from Borisenko and collaborators, and there are, of course, in the literature, many Ironbase measurements, but what I want to show you here is the Fermi surface around the gamma point, where one observes that the inner Hall pocket is strongly renormalized with respect to what we obtain by doing, for instance, LDA calculations. And in fact, this just to see that there is a strong, there is basically the inner Hall pocket shows a flower-like basically shape. So I'm showing here for the experiments just to see this strong renormalization. Now, a theory that has been very successful in describing these effects of correlations in these iron-based superconductors is dynamical mean field theory, which yesterday there was a session on where this was in fact discussed. And the idea of dynamical mean field theory is to replace the system of interacting orbitals into basically a system of one central site, which is dynamically interacting with a path given by the rest of the sites. And in fact, this combination of dynamical mean field theory with density functional theory has been able to describe many trends observed on the correlations in these materials. So for instance, going back to the Fermi surface description, what we see, these are the LDA calculations, these are LDA plus DMFT. We see this trend of renormalization of these inner Hall pockets getting more shrunk as it is being seen in experiment. But what is a most important result of this type of calculations is the fact that the correlations are orbitally selective. So different orbitals show a different degree of correlation. And there is in fact a recent review by our organizers on these effects of orbital selectivity. And there is also, in fact, this new concept of Hund's metal, which also applies nicely to these materials. So the second feature that I wanted to mention that also the DMFT is able to very nicely describe is this transfer of a spectral weight creating Hubbard bands. And here I'm showing results for iron selenium, which is one of the materials thought to be most strongly correlated, where I'm showing the photoemission experiments from Amalia Coldea, Matt Watson and collaborators. And we did here DMFT calculations just to show that one can identify this transfer of a spectral weight as a lower Hubbard band. And even more information can be obtained from these calculations by doing, in fact, this orbital, by looking at this orbital selectivity, what is causing, which orbital is most correlated, showing this effect of the lower Hubbard band. However, even that there is a lot of success in these type of calculations, there are features that in principle this conventional type of doing DMFT, so what we call the one-side DMFT, is not able to reproduce. So DMFT, the one-side DMFT, can describe exactly local correlations, but has no information on non-local correlations. And there is an effect that was already seen a long way back by in some family of these, in some materials of this family of iron-based superconductors, which is what it's called the Bluray shift. So the Bluray shift is the following, that the renormalization of the bands at the gamma and at the M point is going in the opposite direction to what a usual DFT calculation would show you. So if this goes in the opposite direction, so there is a shift to the blue and a shift to the red, this cannot be explained in principle in terms of theory that includes correlation effects only at the local level. So therefore, this was type of experiments was calling for a description where non-local correlations, so momentum-dependent correlations are included. And in fact, there are a few reports on scattering rates where it is claimed, these measurements, it is claimed that there is a strong momentum dependence. So what we did here is to consider a different type of approach to calculate the self-energy dependence that includes also a momentum dependence, not only frequency dependence. And this is by considering the two-particle self-consistent method, which was initially introduced for the one-band Hubbard model by Wilk and Tremblay. And this method, the idea of this method is to start, in fact, by analyzing two-particle correlations and doing some approximations to them. In the way that these approximations are done is by fulfilling different type of sum rules. And at the end of the day, by doing this type of approximation, which is valid for weak to intermediate coupling, one can obtain, in fact, these momentum and frequency dependent self-energies. So we applied that to lithium iron arsenic, and here I'm showing this is the results of the band structures of the Fermi surface by DFT. And when one applies this combination of DFT with this two-particle self-consistent method to obtain the effect of the self-energy, what one obtains is in fact a result, a shrinking of these inner hole pockets, very similar to what is being observed experimentally. And moreover, what is very interesting is that if we now average these results, we do the momentum average, what we obtain is the result of DMFT. So in fact, these two methods, even though these are two type of approaches, different approaches to obtain self-energies, one can obtain the other by doing an average of over the momentum. So let's look now at this red-blue shift or blue-red shift, depending on where you define the blue and the red. How is this described by this type of approach? So what I'm showing here is the band structure. In these green lines is the DFT band structure for lithium iron arsenic, where I did a rescaling of 2 in order to be able to compare better the bands. And the color mapping is the result of this DFT plus TPSC, where yellow means more intensity. And one can see, in fact, indeed, there is this shifting down of the bands at the gamma point and the shifting up towards the Fermi level at the M point. So this blue-red shift is well described by this type of approximation. And the point is that the reason why there is this blue-red shift is because of spin fluctuations at the vectors 0, pi, and pi 0. So that the contribution at gamma and the contribution at M are of different signs. And that's why there is this red-blue shift. So we have also calculated the energy dependence of the quasi-particle lifetimes because we could compare with experiments. So these are experiments by the group of Véronique Bluray, where what I'm showing here is the energy dependence of the quasi-particle lifetimes as I go from gamma to M. So let me show you the one. So this is the inner hole pocket is named by 1, and the inner electron pocket named by fear. These are the red pockets, and these red pockets have a rather linear behavior. I mean, this can be observed here also in these calculations because it looks very incoherent. So this is the result of the experiment. And these are the results that we obtained with TPSC. So we also obtained this type of linear dependence in omega. While the pockets, the whole pockets at 2, so basically these outer hole pocket and these outer electron pockets, they have more quadratic behavior, as it is also seen by experiments. So these theories seem to capture these features observed in Ironbase. So that with this type of calculation, what we can say is that a momentum dependent type of effect in the self-energy is able to explain many features of these Ironbase observations. I should mention also that very recently, Kim, Antoine George, Gabi Codley, and collaborators, what they did is a different kind of calculation. So they did basically GW plus what they call Anzac DMFT, so that they are including all contributions of the long-range part of the Coulomb repulsion. And by doing this type of approach, they seem also to be able to explain this type of features. So that here, I think this would be an interesting subject for discussion. One scenario, which is the scenario I am presenting, is more describing this type of effects in terms of the low energy spin fluctuations, while the scenario 2 is describing this type of effects in terms of the long range part of the Coulomb repulsion. So this, I leave it as an open discussion. Let me go now in my last 5 minutes to the topology part of my talk. And I'm now changing the iron-based superconductor I would like to focus on. So I'm going to go into the so-called 1144 materials. And what I want to show you is that by considering a combination of spin-orbit coupling, magnetism, and the very special structure of these materials, one can predict the presence of double Weyl points. Let me show you that step by step. So first of all, the materials I'm talking about are, for instance, calcium, potassium, iron 4, arsenic 4. So these materials have the same structure as the 1 to 2 materials, but what we have in this case is that there is an alternation of cations, so calcium, potassium, calcium, potassium, what makes this a structure that the unit cell is 2 iron planes per unit cell. And because of these different cations, we are breaking explicitly the glide symmetry that is otherwise present in all iron-based superconductors. So what we have in this material is there is no glide symmetry. And because there is no glide symmetry, there is also no iron plane inversion symmetry. However, the symmetries I will concentrate on in order to get to these Weyl points is the fact that this system has a C4C symmetry along this vertical axis and still keeps an inversion symmetry which is centered at these cations, calcium or potassium. And the bands that I want to now concentrate on, so contrary to the topological effects that we, for instance, saw yesterday, where there was a crossing between a D and a P band, so a D band of iron and a P band of arsenic, what I will be concentrating today is only on D bands. And on this path along the Bluray zone, the MA path, which is the path along from pi pi 0 to pi pi pi. So let's first do symmetry analysis along this path. So what I'm doing now is by considering basically these special symmetries of calcium, potassium, iron 4, arsenic 4, I just can evaluate the irreducible representations of the bands along this path of the Bluray zone. And let me concentrate on this MA path. So what we have, if we consider the fact that I have a glide plane symmetry broken, that I have a C4C symmetry, and I have an inversion center at the calcium or potassium, what we will expect is to have nodal lines along MA, which are fourfold degenerate, twofold because of the C4C symmetry and fourfold because of the Kramer's degeneracy. And I have two sets of them because calcium, potassium, iron 4, arsenic 4 has 2 iron layers per unit cell. So now what we want to do is basically this fourfold nodal line, we want to break all the possible degeneracies to get at the end of the day just non-degenerate bands where a possible crossing can happen. So one way of breaking this degeneracy is by applying a magnetic field along Z. So we are going then to break the Kramer's degeneracy, and we will just get here twofold nodal lines. Another way of breaking this degeneracy is by including the effects of spin-orbit coupling in this system that will also break this degeneracy into twofold bands. So if we combine the two effects, spin-orbit coupling and an application of an effect of a magnetic field along Z, at the end of the day, indeed, we are going to have non-degenerate bands. And what the symmetry analysis is telling us that there is the possibility of having a crossing along this MA direction, either a crossing where the bands have the same spin polarization, but opposite angular momentum polarization, and this will give rise to a double Weyl point, so in fact, a pair of double Weyl points, or in the case that the magnetic field is not that strong, we can have a crossing between bands that are of opposite spin polarization, and then we will have a Weyl point of charge plus or minus 1, so a pair of those. So now we go to the real system and do the calculations, and we apply the magnetic field along the Z direction so that the the polarized iron has a magnetic moment of about 0.6 mu Bohr. And by doing this calculation, what we find is indeed that we get a double bial point along this line. So at plus kz and minus kz, and in order to show you that it is indeed the double bial point, as the symmetry analysis is telling us, analyzing the band structure near this double bial point is indeed a band touching, which is quadratic in the kz-kx plane, and it's linear along the it's quadratic along the ky-kz and linear ky-kx and linear along kz. And the two bial points, this is a picture of the very curvature, so the flux of the very curvature, which shows us that one, it is basically the flux is going out of the bial point, and in the other one, it's going in. So one is a source and the other one is a sink. And one can also calculate basically these Fermi arcs that are connecting these two bial points. So with that, and I think my time is over, I come to the end of my talk. So the second part was to show you that it is possible to have magnetic field induced double bial points in these 1144 materials by application of a magnetic field. And in fact, the bial points that we found are very near the Fermi surface. So for instance, by using the doped, the doped materials, so in order to bring down the Fermi level, one could have these bial points at the Fermi surface. And what it may be very interesting is to investigate the interplay of superconductivity and topology. And the first part, what I showed to you is that the effect of non-local correlations in iron-based superconductors in order to understand some features of the spectral function in these materials. And with that, I would like to thank you for your attention.
Thank you, Rosa, very much for this great talk. Any questions from the audience? Well, while the audience is thinking of questions, may I just ask one question to start? Sorry, and then David, yeah. So Rosa, so is the splitting of the bands in the last part just the Zeeman, the energy scale on the order of the Zeeman splitting? So you want to resolve this?
Yes, so exactly, this one, right? This. Okay, so the order of the Zeeman splitting, in principle, if I want to get this double bial point, is rather large. So it means I have to apply rather strong magnetic fields. So that's why what we did is so basically we extracted the order of magnitude from the polarization of the magnetic moment. So we need to polarize them along the z direction with a magnetic moment of 0.6 mu Bohr. So it's going to be large magnetic fields, but I think it's doable, at least with the sources that one has. So I think it's optimistic. Otherwise, of course, what you will get is single bial points, which is also an interesting. So to reach the double bial points, the magnetic fields have to be large.
I see. Thank you. I think next, David, do you want to ask your question?
Hi, this might be a bit dumb, but I'm not sure I understood what's the difference between a double Weil point and a Dirac point. Is there a brief way to clarify that?
Yes. So the double Weil, okay, so the double Weil point is in this case, these are Weil points that come because the bands they have non-degeneracy, while in the Dirac points we have degenerate bands touching, and in this case we have bands of the same polarization, but it's the angular momentum which is opposite. And this gives rise to these double Weil points, which means that along in the direction perpendicular to z, so along the kx and ky, I'm going to have a quadratic band touching, while along the kz direction, I'm going to have a linear band touching, like in the single Weil points. I don't know whether this was clear.
So was the major distinction about the band structure, like the quadratic?
The basic distinction, so maybe let me show it here.
Or the angular momentum?
the angular, so the major distinction is that a double violet point is a quadratic band touching, while a single violet point is a linear band touching.
I see. Okay, thanks.
And then Timiao.
Yeah, was a very nice talk. So just sort of going back to this theme of what is universal across these ion-based superconductors and what is not.
Yeah.
I thought it would be to the first part of your talk.
Yes.
So lithium ion arsenic. So it's interesting to ask, how does it compare with FeTe SE, a material which is of a lot of interest for a variety of reasons. So there, actually, the chair showed that you have this orbital selectivity, but the gross level, you can just raise the temperature and see that some of these orbitals, the spectral weight just go away, and the others don't, right? So dxy is where it goes away, and there's some temperature scale for that. Now, and that was one of the sort of indications where local interactions play an important role. Now, in lithium ion arsenic case, that the APES experiment was also done, and the temperature scale is a bit higher, 200, slightly more than 200 Kelvin, but also the XY orbital spectral weight goes away at that temperature. So I just wonder whether in this discussion of non-local correlations contributing to the renormalization of the electronic band structure here versus local ones, how does that seemingly zeroth order feature factor into the consideration for you?
Yeah, I mean, this is a very good point, because that's why we're having all this discussion with Antoine and with and Gabi, because you want to find. I agree with you that it's not a simple problem, okay? And in fact, you are talking about iron selenium, tellurium, iron selenium sulfur, all these systems. In fact, the iron selenium is in some sense is more complex than, in my view, than lithium iron arsenic. It's more complex because we have there more features that we still don't completely understand, like, as you say, disappearance of depending on the temperature, also disappearance of some spectral weight. That's why we chose this material, which seems to be I classify it as less strongly correlated. I mean, it's correlated, but less strongly correlated. And maybe we don't have to deal with these extra features. But I completely agree that it is. So what I saw here is that this could be a scenario to understand some of these features, but probably not. It's not. With that, we are not settling the whole problem. And that's why we're discussing also with Gabi, what about the long-range Coulomb interactions that we know that they are also influencing that. And at the end of the day, the question is, which of all these different contributions is the one that maybe dominate, or it's all of them at once? Or this, I think, is something we need to think about a little bit further. But it's not a simple problem. I just wanted to show that by doing such a type of approach, one at least is able to understand some of these properties in terms of spin fluctuations. This is basically what this approach is giving you, that spin fluctuations are important in these materials. But it's not the only ingredient. We need to also include charge fluctuations, and the charge fluctuations in this type of approach are only included at the what I call at the low energy level. So wherever I do the cut, so it's not an integration over all energies, and this is something one has to work out still.
Yeah, fair enough. So continue this discussion.
Thank you. And one more question from Peng Cheng.
Yeah, so I was very curious on your last part. When you turn on the magnetic field, you induce this well points. So what are the sort of experimental signature you might expect from spin fluctuation point of view? Assuming you do such a Duncan experiment, putting a large magnetic field.
Yes. So what I expect, if you put a large magnetic field, and then you are able to basically separate these these bands so that you don't have a mixing of the two polarizations.
Right, right.
And now I'm showing it here. This of course depends on the features of your material, but in this material, what I expect if you put a magnetic field and you are able to bring this on the surface, so by using the dope, you should be able, depending on the experiment you do. So if you do a transport experiment, so you should be able, for instance, to see these effects of these Fermi arcs. If you do an Ironbase experiment, the question is with magnetic field, I think there is no possibility, right?
Right.
So there is no way, but transport, yes. So one would see, in fact, a lot of anomalies in transport experiments. For instance,
I'm curious on the spin fluctuation. I mean, what would you expect the spin fluctuation will respond?
Yeah. Okay. So this system, and in fact, there's an ingredient I didn't talk about. This system we know. This system we know that. In fact, when you dope it, when you electron dope it, it shows this order, this spin vortex order. So we know that and there are, in fact, for this material, there are NMR data that show these spin fluctuations that come from a vortex type of fluctuations. So what we expect is that these vortex fluctuations are going also to influence the presence of this type of bile points. Is this the question you are posing?
Yeah, no, yeah. I mean, basically, this stuff is known to have an income. Believe it's incommensurate, some sort of incommensurate spin fluctuations, right, or something.
No, vortex. This system is a vortex. So this vortex will definitely enhance this type of topological points. So this type of features.
Okay. Yeah. Thank you.
So they work towards it.
Sorry, can I just ask one last question based on the slide?
Yes.
Sorry.
On
so
this one?
Like, yeah, the slide. So it seems like so every set of bands from M to A has this property, right? Is that just
well,
due to the
from M to, at least you can find, exactly, in principle you can find many of these bunches of bands where you could indeed find these features. Yeah, I mean, all these D bands, these are all D bands. So the only problem is that, of course, if you have a lot of hybridization with, let's say, arsenic, then it's going to be more obscure to find these crossings. So, but it's true, from the symmetry point of view, you should be able to find these in all these bundles of D bands that are along this path.
Okay, thank you very much. Thank you for this very nice talk, Rosa.
Thank you very much. So I'm stop sharing.
Yes, and then next we have Vidya Madhavan from UIUC. Vidya, you can start sharing your screen.
Okay, let me actually turn on my video somehow. There.
Great.
Hi, everyone. Good to see you all.
You want to play and see if we can get the correct screen?
Yeah, what do you see?
Perfect, that's the right screen. So
okay.
We have Vidya, right. So I